So hello everyone, welcome to today's lecture. So in today's quantum chemistry lecture, I will discuss the variational quantum eigensolver and the couple cluster ansatz. As we'll see later, the variational quantum eigensolver offers a different way to simulate quantum chemistry on quantum computers than the quantum phase estimation. It does so with an approximate wave function ansatz and classical optimization techniques. So before we start today's lecture, let's do a brief recap of our last two lectures. During our last two lectures, we introduced the quantum chemistry problem and discussed how the quantum phase estimation algorithm could be implemented on a quantum computer to solve the exact ground state energy of a molecular system. So here I show the circuits for the quantum phase estimation, and it works in 4 steps. Firstly, we initialize the state register, which needs to be initialized to a state that overlaps significantly with the ground state, such as a Hartree-Fock state. Secondly, we perform the control U operation, in which U is a time propagator, and then we perform an inverse Fourier transform before measurements, and then read out the energy. All right, so the advantage of the quantum phase estimation is that it will always yield the exact results. Frankly speaking, we have also discussed some techniques that introduce approximations to the Hamiltonian, such as the low-rank approximation. However, given a Hamiltonian, the quantum phase estimation algorithm will always yield the exact energy. Furthermore, the number of measurements needed is low, which is the same as the number of ancillary qubits. Yeah, so the advantage of the quantum phase estimation is that it will always yield the exact results. So frankly speaking, I think I already discussed this. Okay, so the disadvantage of the quantum phase estimation algorithm is also very obvious. It usually results in extremely long circuits as one needs to implement multiple powers of the propagator. Such a feature makes it less suitable for near-term noisy devices, since the circuit length is limited. In other words, QPE will be the choice of algorithm in long-term fault-tolerant quantum computing, but its application in near-term noisy quantum computers is limited. Okay, so let's start today's lecture by introducing the variational quantum eigensolver. So the starting point of a variational quantum eigensolver algorithm is to choose an ansatz psi. This ansatz could be implemented on a quantum computer, and such an ansatz contains a set of unknown parameters, theta here. As such an ansatz will translate to a variational circuits on a quantum computer. So in the second step, we run the circuits for many times and gather the measurements results. And for the measurements results, we could then compute the energy expectation value defined on the defined for the wave function under the current parameter set. And the third step is that we feed energy into a classical optimizer. The classical optimizer will then find the parameter change delta theta that lowers energy expectation value. The reason that we want E to be lower is due to the variational principle. As you may recall, the variational principle tells us the lower the energy, the better the wave function. So with the parameter change, we update the parameter theta in the variational circuits and then go to the second step. This is then repeated until the energy has converged, at which point we have found the best wave function parameters that are closest to the exact ground state. Now let's compare the variational quantum eigensolver and the quantum phase estimation. As we mentioned, the QPE always yields the exact energy. However, the energy predicted by VQE is not exact. Since we have chosen an approximate wave function ansatz for VQE, its accuracy will depend on the quality of such a wave function ansatz. For example, if you choose the Hartree-Fock wave function for VQE, then the result you obtain is at best at Hartree-Fock level of accuracy. So the advantage for VQE or QPE is that it does not require a long circuits. All we need to implement for VQE is the variational circuits for only once, whose length depends on the choice of the ansatz. We do not need to perform the control U operation raised to a large power as in QPE. However, since VQE needs to compute the expectation value, it needs many more measurements than QPE. As we shall see later, one needs to perform measurement for every term in the Hamiltonian expression, which significantly increases the number of measurements we need to do. So in the end, VQE requires one to use the classical optimization techniques, while QPE does not. This adds another layer of difficulty for VQE, since nonlinear optimization is not a trivial problem to solve. Fortunately, this is a very advanced field, and the knowledge is directly transferable. So as we have seen now, the most important piece of the VQE algorithm is the choice of the ansatz. It needs to satisfy several criteria. Firstly, it needs to be capable of being implemented on a quantum computer. Otherwise, it is not useful for us. Secondly, it needs to be accurate enough so that we're not introducing a drastic approximation. Third, it cannot be simulated efficiently on a classical computer. Otherwise, we do not need to use a quantum computer for such a problem. As you can see, the Hartree-Fock ansatz is not a good choice for VQE, since it is not accurate enough, and we know how to simulate it on a classical computer. So one choice of the VQE ansatz is a unitary couple cluster ansatz defined here. So in a nutshell, the unitary couple cluster ansatz operates the exponential of the so-called cluster operator minus its adjoint to the Hartree-Fock state. The cluster operator includes all the possible excitations from the Hartree-Fock state, such as singles, doubles, triples, and so on and so forth. Each excitation is associated with a parameter, the T amplitude. Since the exponential of the cluster operator minus its adjoint is a unitary operator, we could implement this ansatz on a quantum computer. So one needs to note here that here the unitary couple cluster ansatz defined in this way, since it includes all levels of excitations, it is an exact ansatz. We will later make approximations to it. Okay, so you might wonder, how do people come up with such an ansatz and why it is accurate? In order to understand this, we need to know the history of the couple cluster ansatz. The unitary couple cluster ansatz is a variant of the traditional couple cluster ansatz. Let's first recall the full CI wave function, which is a linear combination of all the possible excitations from the Hartree-Fock state plus the Hartree-Fock state itself. So at the early days of quantum chemistry, people have noted that the importance of these excited configurations decay with excitation levels. For example, a 6th level of excitation is much less important than a double excitation. So why don't we just truncate the full CI wave function to certain excitation levels? For example, let's just truncate it to doubles. This gives the CISD wave function. So the CISD wave function contains only n to the 4th terms, in contrast to the exponential number of terms in the full CI wave function. However, this is actually a very bad wave function that nobody uses these days. So why is it? So the reason that the CISD is a bad wave function is because it does not satisfy size consistent. Suppose we have two systems here, A and B. The two systems are separated far away from each other so that there is no interactions between them. We will not perform two calculations for a chosen wave function ansatz. First, we compute the energy on system A plus B as a supersystem, and then obtain the energy EA plus B. And then for the second calculation, we compute energies separately for the system A and B, and the energies are EA and EB. Okay, so for a wave function to satisfy size consistency, EA plus B must be the same as EA plus EB, which is expected since there's no interactions between system A and system B. Such a property is satisfied by the exact wave function and the Hartree-Fock wave function, but not by CISD or any other truncated full CI wave functions to a certain excitation level. So due to the failure of CISD and its breakdown of size consistency, people have developed the traditional couple cluster wave function. It is written in this way: by applying the exponential of the cluster operator to the Hartree-Fock state. Note that the difference between the traditional couple cluster and the unitary couple cluster is that the exponential of the cluster operator is actually not unitary. So this wave function, the traditional couple cluster wave function, could not be implemented on a quantum computer. So we now truncate the cluster operator to double excitation level. This gives us the CCSD wave function, couple cluster with singles and doubles. One could prove that the couple cluster wave function or any other truncated couple cluster wave function is size consistent. So more importantly, since the cluster operator appears on the exponential, once one expands the exponential with the Taylor series, we could find that it not only contains singles and doubles, but it contains all levels of excitation. For example, triples, written this way, can be triples are composed by a product of singles and doubles. This makes a CCSD a much more powerful ansatz than CISD, which only contains singles and doubles. So the question is, how can we solve for the T amplitudes for these parameters for the couple cluster ansatz? One first try would be to use the variational principle and optimize the energy expectation value as a function of theta. Theta here are the T amplitudes. However, it turns out that the cost for evaluating the energy expectation value for a traditional couple cluster wave function scales exponentially with system size. So we cannot do this. So the second try that actually works is to solve the projected Schrodinger's equation. By left projecting the Hartree-Fock state times e to the minus t, we could compute the energy. And then by left multiply by the double excited configuration times e to the minus t, that's written down in this equation in the bottom, we could solve for the double amplitudes, and it's similar for the single amplitudes. Yeah, so I would like to pause here and then answer any questions regarding like the classical traditional couple cluster on that.
In this page, at the bottom of the at the bottom, I can understand why the equality becomes 0 for
T.
T.
Okay, so the reason that the equality, the reason that there's such an equality here is you can see that if you left multiply by e to the minus t to the Hamiltonian, and then the let me see. Yeah, so suppose suppose you agree that this the couple cluster is an exact wave function, and then the Schrodinger's equation must be satisfied. And then if you left multiply by e to the minus t, on the right here, it cancels this e to the t, and it gives you e times Hartree-Fock, right? And then you left multiply by this excited configuration. On the right here, it becomes the energy, which is just a scalar, multiplied by the overlap between the excited configuration and the Hartree-Fock configuration. And then because the orbitals for because these orbitals, the molecular orbitals, are orthogonal to each other, any excited configurations is actually orthogonal to the Hartree-Fock configuration, so that the overlap is actually 0. That's why we end up with this the bottom equation.
He's asking if h and e to the t commute each other. I don't think so.
No, h and e to the t does not commute with each other.
Maybe he's questioning how come we get the equation in the center of your slide, like h e t e to the t Hartree-Fock state is equal to e to e times e to the t. Yeah.
So this so I mean this equation or this one?
The top one,
this one. Okay. Okay, this is just the Schrodinger's equation. You have to assume that the couple cluster wave function is the exact wave function, so that it satisfies the Schrodinger's equation. So you have to make that assumption first to get this equation. Of course, if you include all the terms in the cluster operator, if you do not make any truncation at all, this equation is exactly satisfied. Then the couple cluster wave function becomes the full CI wave function. But if you make any truncations, it is in general not satisfied. So because the wave function is no longer exact. But then we still make that assumption otherwise we cannot get these equations to solve for compute energy or solve for the amplitudes. Okay, so how does the couple cluster wave function work? Here's an example of the potential energy surface of a nitrogen molecule. The nitrogen bond is a triple bond, which contains 6 electrons. Stretching the triple bond poses a very difficult problem for quantum chemistry. We compare the traditional couple cluster, the variational or conventional couple cluster, or the variational couple cluster, and the unitary couple cluster with singles and doubles to the full CI results. All the data here are from the classical computers. The variational couple cluster, the variational CCSD is done by actually performing the minimization of the energy expectation value of CCSD wave function with exponential cost. And similarly for the unitary couple cluster, since the system is small, we can afford that calculation with a classical computer. So as you can see that if the bond is not stretched, if you look at this region, all three methods works very well, and the energy produced is very close to that of the full CI results. However, as one starts to stretch a bond, the traditional CCSD goes to a very unphysical solution with energy that is much lower than the full CI energy, while the variational and the unitary CCSD still produces accurate results. So in other words, the conventional or the traditional CCSD works well in the so-called equilibrium region where the bond is not stretched, but behaves highly unphysical once one starts to stretch bonds. To the contrast, the unitary couple cluster works well in both regions. This is a general problem for the traditional CCSD. Namely, it cannot describe strongly correlated systems, such as the breaking of a triple bonds. Strongly correlated systems go beyond to the multiple bond breaking scenario. It also includes high temperature superconductivity, transition metal oxide, and excited states. And traditional CCSD tends to work badly in these cases. Okay, now we basically know why we want to use the unitary CCSD on us. Namely, that it produces accurate results for not only the equilibrium position, but also for strongly correlated systems. Let's see how we can implement it on quantum computer. The first step is, of course, to prepare the Hartree-Fock state, which is trivial, and we have discussed this before. And the second step is to implement exponential of the cluster operator minus its adjoint. This could be done by first performing a Jordan-Wigner transformation for the cluster operator T, and then turns it into a sum of Pauli matrices and implement each term individually on a quantum computer. The last step is to perform measurements. A schematic picture of the circuit is shown here. After we compute the energy, we feed into a classical optimizer, and then we update the T amplitudes. We then run the circuits again, and so on and so forth until we have converged the energy. So now you might want to know how we could compute the energy. Consider this concrete example. Suppose the Hamiltonian can be written as a sum of these 6 terms after the Jordan-Wigner transformation. Then the energy expectation value would be the sum of expectation value of these 6 terms. The first term is a constant, so we don't consider that. And the second to the fourth term are easy to compute since they only include the Z matrices, which is diagonal in our computational basis. For example, for the first term, we just need to measure the first qubit and compute the expectation value. And then things becomes a bit more complicated for the last 2 terms, since neither X or Y matrices are diagonal in the computational basis. Therefore, we need to perform an additional set of rotations before measurements. For example, for the XX term, we use the H gates, the Hartmann gates, to rotate into the Z basis and then perform the measurements. You could see that in the most general case, each term will require a different set of rotations and a different set of circuits. This is why VQE needs many more measurements than QPE. So the last piece of puzzle will be to optimize energy classically. There are many choices here, and one is called the simultaneous perturbation stochastic approximation, or SPSA short. In the nth iteration of SPSA, we change the parameter by subtracting a positive number A times a vector G. Here, A is a learning rate that quantifies how confident we are when updating parameters. The vector G estimates the energy gradient with respect to parameters. So the vector G can be computed as follows. We randomly perturb the current parameters by C times delta, in which delta is a random vector sampled using a zero mean distribution, and C is a positive number. We then further perturb the energy by epsilon. We then compute the gradients with a finite difference approach. The SPSA could be considered as a noisy version of the gradient descent optimizer. Here I show a schematic picture comparing the SPSA and the gradient descent optimization process. SPSA is known to be robust to noise, since every parameter is already being shifted, and additional shifts due to noise are less likely to hinder the optimization process. This makes it very suitable for noisy quantum computers. Okay, so besides ground state, we could also simulate excited states using the CCSD wave function. First, let's consider the traditional conventional CCSD. Once we have solved for the T amplitudes for the ground state, we could then perform singles and doubles excitations out of the ground state CCSD wave function. We then diagonalize the Hamiltonian matrix formed in the space spanned by all the singles and doubles excitations out of the ground state CCSD wave function. By doing so, we obtain all singly and doubly excited states. So such a technique is usually called the equation of motion method. The idea is to perturb around the ground state wave function and find excited states in the perturbed space. Here, on the bottom here is a table that compares different excited states from these three different excited states obtained from the EOM equation motion CCSD to experiments results. The experiment result is shown by this column on the right. As you can see, the EOM CCSD produces very accurate excitation energies compared to the experimental results. And you might wonder what these like DZP, PBS are. So they indicate different set of basis set. So in order to compare with experiments, you have to use a large basis, and the error tends to go down with the number of basis functions. So you can see that as we go from small to large basis, the error in the excitation energy starts to go down and then start to convert to the experimental results. All right, now let's looking at the VQE, how we can do VQE for excited state on a quantum computer. The same idea of equation motion still applies here. Similarly, we form the matrix in singly and doubly excited space of the ground state VQE wave function. Instead, at this time, the matrix elements are not computed on a classical computer, but measured on a quantum computer. For example, the SS block of this matrix could be written in this way, and you will notice that this is just an expectation value of a particular operator, which could then be measured in the same way as we measure the energy. So although our discussion so far has been focused on the unitary CCSD ansatz, the UCCSD is not a unique choice for VQE, and people have developed other ansatzes. One example is the hardware efficient ansatz that had gained a lot of interest recently. So unlike the unitary couple cluster and singles and doubles, which is motivated physically, the hardware efficient ansatz takes advantage of the quantum hardware. They are usually defined as repeatedly applying the single qubit rotation and the entangler block to an initially all zero state. The single qubit rotation performs the basis change, and the entangler puts correlations in between different qubits to simulate electron correlation effects. So compared to the unitary CCSD, the hardware efficient ansatz is more efficient to implement on a quantum computer, and it usually results in less number of quantum operations. However, as mentioned before, it is not physically motivated, and the results and the errors will be difficult to analyze. So people have tried to use multiple kind of entanglers. They could include this 2-parameter and this 1-parameter and no parameter entanglers. Different choice of entanglers results in different circuits. And in principle, as long as the entanglers conserves particle number, it is going to be a valid entangler. Here shows a comparison of the hydrogen potential energy surface predicted by these 3 different entanglers to that of the unitary couple cluster, singles and doubles wave function ansatz. As you can see, they are generally less accurate than UCCSD due to the fact that they are not physically motivated. Okay, so in this lecture, we have discussed the variational quantum eigensolver. The variational quantum eigensolver offers a different way to simulate quantum chemistry than QPE. Compared to QPE, VQE has significantly shorter circuits, which is more suitable for the near-term area. However, there is no free lunch. The short circuits of VQE comes with a cost of a large number of measurements and the requirements for classical optimization techniques. In terms of the approximate wave function ansatz, the unitary couple cluster with singles and doubles could be straightforwardly implemented on a quantum computer, and both ground and excited state could be simulated using the variational principle and the equation of motion techniques. We have also discussed that the UCCSD is not the only choice for VQE. One could also use a hardware efficient ansatz with different choice of entanglers. However, we must be cautious for the hardware efficient ansatz since they are not physically motivated. So going forward, we might want to ask ourselves that whether VQE could be made exact and free of the classical optimization techniques, while maintaining its nice property of short circuit length. This is a very active research field, and we hope to discuss some of the advanced work in the next lecture. All right, that's it. Then let's answer some questions before we do the hands-on session.
Thank you for your clear lecture. And I wonder why the hardware efficient ansatz is called hardware efficient. Is it specialized on the IBM-Q or IonQ, such a specific computer?
I believe the hardware efficient ansatz. Where is it? This one. This is initially developed by IBM. So why is it called the hardware efficient? Because it just takes advantage of the quantum hardware. So you do this single qubit rotation, and then you do this entangler blocks that entangle like different qubits. So it takes advantage that we can basically perform this U rotation and then like 2 qubit gates on quantum computer. So it takes advantage of that, and it does not like think too much about how that circuit is like what that circuit mean physically, what kind of ansatz it really like prepares. So then I think that from my perspective, that it usually results in like much less number of like parameters or like circuit lengths compared to just direct translation of the unitary coupled cluster ansatz. I think that's why it's called the hardware efficient, because it's very straightforward to think it in terms of like quantum circuits, right? So you just think of like, instead of like preparing a wave function ansatz with a second quantized like the fermionic notations, and then translate that into a quantum circuit, you directly think of quantum circuits and then just prepare like a variational circuit with some parameters and hope that could give you enough entanglements that would describe like the physical system you will simulate.
What is a good physical reason that unitary coupled cluster is better than the conventional coupled cluster?
Okay, so the physical reason for that, so there's nothing wrong with the conventional coupled cluster ansatz. So the unitary coupled cluster and the conventional coupled cluster has basically the same form, and then they should have the same like flexibility. But the reason that unitary coupled cluster is better than the conventional coupled cluster is because with a quantum computer, we could do unitary coupled cluster variationally. We can like optimize the parameters with variational principle. But that's something we cannot do on for like a classical computer. So that for classical computers, in order to use this coupled cluster ansatz, we have to solve the projective Schrodinger's equation. So there are a lot of research in this. And then the conclusion that people find is that it is not really that the coupled cluster ansatz is wrong for conventional or traditional coupled cluster, but it's actually the way we solve for the T amplitude and the energy is actually wrong for strongly correlated systems. For strongly correlated systems, we need to do things variationally, not projectively. Let's, for example, if you can do coupled cluster, if you can do conventional coupled cluster with variational principle, you will find that it is as good as unitary coupled cluster. But then the cost will be exponential scaling. Similarly for a unitary coupled cluster on a classical computer. So it's not really that the unitary coupled cluster wave function is much better than traditional coupled cluster. It's just that with a quantum computer, we can do unitary coupled cluster variationally. That gives us the power to explore the flexibility of this particular wave function ansatz.
So I have a question about the like general idea of the variational algorithm. So like what we do is to explore the Hilbert space with the some parameter with theta. So how can we guarantee that like if the system size becomes bigger, like if you like simulate the more like the complex molecule or the more orbitals, I believe the Hilbert size of the Hilbert space will like the exponentially bigger. And how can we guarantee that the subspace we're gonna explore with the like this precise theta is like have some overlap with the ground states of the molecule we want to explore?
You're talking about the ground state or the excited state?
Like whatever like target, like the because like we're not gonna explore the whole Hilbert space with the like the finite number of the theta.
Right. Right. So yeah, I see what you mean. So how can we guarantee we so how can we guarantee we have a good wave function that is compact enough, but it offers like high level of accuracy? So this really need like you to carefully design the wave function so that it's like physically motivated. For example, the unitary couple cluster, it does like the exponential operator acting on the exponential of the cluster operator acting on the Hartree-Fock. And then the thing that people have understand these years is that although like the Hilbert space is the large space, it's not like every piece of the Hilbert space is important. So usually the most important pieces are the singles and doubles excitations out of the Hilbert space, because out of the Hartree-Fock state, because that's where like that's the configurations that directly connect to the Hartree-Fock state. And then the couple cluster ansatz have those like free parameters for all the singles and double excitations. And then it also gives you like the other excitation, like the triples and then the quadruples, the hexadubles, by multiplying. Like, for example, triples can be like multiplication of singles and doubles, and quadruples can be like multiplication of doubles and doubles. So that they also have these high level excitations that can like get you to like a larger part of the Hilbert space. But then still, like there's no like theoretical proof that the couple cluster wave function will work in any cases. So like people have developed like different like more advanced techniques to dynamically adjust the couple cluster wave function so that we make sure that we get like error down to certain levels. So in general, for more complicated systems like the strongly correlated systems, like by merely applying use couple cluster may not be sufficient, and then we may figure out only singles and doubles may not be like sufficient, and we might need to add triples, and then we do it in a dynamic way so that we do not add all triples. And so in this way we can like grow our ansatz to make sure we always, for example, like describe describe the physical system accurately to a certain level of accuracy.
Is VQE applicable to only ground state calculations? I think it's no, right?
No. So VQE can be applied to excited state as well. Like one way to do so is like is with the equation motion technique that I have described. And there are other like techniques you can, for example, perform energy minimization or energy optimization with a constraint, so that you're targeting certain excited state. The constraint could be like that state to be orthogonal to the ground state. So they have very small or zero overlap with the ground state. So we can like excited state then becomes like a energy optimization with a constraint. So it can be applied to both ground and excited states. But excited states are in general more complicated than ground state.
I have one more question. Like it could be just like the question for like general VQE. So is there any like holy grail for the quantum chemistry calculation we want to do with the quantum computer? Like the, for example, like the Schur's algorithm, everyone wanted to like the hack the 2048 out of state like key, and they say like we will need like millions of qubits and billions of quantum gates for that. Like so. What would be like holy grail for this quantum chemistry, and what is the like corresponding hardware we will need for that?
That's a good question. So the holy grail. So I heard people have talked about the Fumoko, like a molecule which is like a transition metal oxide, a transition metal like catalyst that can be used in like for example like nitrogen fixation. So if you can solve that problem, you will be able to like feed billions of people in the world. I think for like a QP quantum phase estimation to like simulate that system. I saw like resources require like 10 to the 14th, like 2 qubits gates to do that. And then, but I'm not sure for VQE how many how large of circuits you need to perform that calculation. I think like people are still like exploring developing different VQE algorithms, and then so trying to simulate that because like VQE in general is not exact. But if you want to simulate that with like exact calculations, like the quantum phase estimation, I like saw like resource estimations like using 10 to the 14th or 10 to the 11th on that order of magnitude of 2 qubits gates. All right, so the first, let's look at the first notebook, which do not require to use a quantum computer. In this notebook, we'll check the size consistency of the CISD and the CCSD wave function, and then test the performance of CCSD for weakly and the strongly correlated regimes. This is not relevant. All right, so let's just perform some imports, and then the important thing is to import PySCF, and then here from PySCF we also import the couple cluster module. Okay, so the first thing we perform an energy calculation for a single hydrogen molecule. We perform both the CISD and the CCSD calculation. And after run this, it will output the converged SCF energy, which is the Hartree-Fock energy. It will compute the CISD and the CCSD energy, and you can see that in this case, both CISD and the CCSD matches to like 8 digits after the decimal points. They are both very accurate in this case. All right, so the next thing we do is we add another H2 molecule that is 100 angstroms away from the first H2 molecule. So they are separated by such a large distance so that their interactions are effectively zero. And by running it, it will also compute the Hartree-Fock energy, the CISD energy, and the CCSD energy. And you can see now that the CCSD energy is actually lower than the CISD. They do not match like 8 digits. And then now we can compute the size consistency error for CISD and CCSD. So we do not need to run a separate calculation for the second hydrogen molecule, since both hydrogen molecules have the same bond length. So the size consistency error can just be computed by subtracting 2 times the energy for a single H2 molecule from the energy of this 2 H2 molecule. All right, so and you can see that for a system that is small, like only 2 H2 molecule, the CISD size consistency error is already 0.06 electron volts, while the error for CCSD is essentially 0. Although such an error looks small, let's see what happens if we continue to add H2 molecule to the calculation. And in this case, we use 5 H2 molecule. And now we compute the energy for Hartree-Fock, CISD, and CCSD, and then we compute the size consistency error of it. You will see that now the CISD size consistency error, now we have like 5 H2 molecules, so that's 10 electrons in total, is now as large as half an EV. So the size consistency error builds up as the system size gets larger. So that what it means is that the wave function, the quality of the wave function deteriorates with the system size. It makes CISD unusable for large systems, which is kind of the goal for quantum chemistry simulations, is to simulate large systems. So that's why CISD is not usable for large systems, because you see that the size consistency error quickly builds up and it consumes all the correlation energy you got by running the CISD calculation. And then to the contrast, the CCSD size consistency error is still effectively 0. Okay, so the last thing is that we test the performance of CCSD for different bond lengths of the nitrogen molecule and see how it performs. So it's sort of like cut out. So the bond length should be around from 0.6 to like 3. So it covers from like the equilibrium geometry to the stretch geometry. And then we basically run the calculation for full CI, Hartree-Fock, and CCSD calculations for each bond length, and especially we want to see how CCSD performs. All right, so if you run this, it will output a bunch of things. Essentially, this is the energy, the Hartree-Fock energy, the CCSD energy, and the CCSD correlation energy defined as the difference between the CCSD energy and the Hartree-Fock energy. It will do it for multiple bond lengths, and then it will essentially plot the results. And you can see that if your bond length is small, so around this equilibrium or squeezed geometry, CCSD basically almost matches exactly with the FCI full CI calculation until like bond length reaches around like 1.75 angstrom. And then we see that we start to observe some very unphysical behavior of CCSD. And if we continue to stretch the bond, the CCSD calculation stops from being converged. And then essentially the results we got in this region are basically garbage. Yeah, so any questions for this notebook?
5 hydrogens and nitrogen. Oh, did you compare these calculations with QP, and also if we use the actual IonQ hardware, are these 5 hydrogens or nitrogen molecule computable with QP?
With QP, so if you want to do them as a whole system, for example, if you want to just treat 5 hydrogen molecule all together, then I think it will be difficult to do it on any quantum hardware for now. If you want to implement the QPE, because essentially, well, yeah, so if you make some approximations, for example, because they are separated so far away from each other, so that the correlations between different molecules, different hydrogens will be basically zero, and then what you end up with is just repeating the circuits for just 5 single H2 molecules. So think about just doing a QPE. Doing a QPE calculation for like a single H2, and then just stack that circuit like 5 times, because like the correlations between like these different H2 molecules are essentially zero. So that is doable as long as you have you have enough number of qubits to store the wave functions for 5 H2 molecule. But if you then bring them together so that they start to interact with each other, it will be very hard to simulate them using QPE on any quantum hardware for now, because then due to the interactions or the correlations, the systems, the quantum circuits tends to get much longer than just 5 non-interacting hydrogen molecule. For H2, that's a different question. So still, if you want to simulate the whole molecule without any like approximations such as active space truncation, I think it will be hard to do it for QPE. If you're willing to do some approximations, such as truncated to like a minimal active space, I think there are some hope to implement it on a QPE algorithm on the current IonQ quantum hardware. But I haven't tried simulating that.
Sorry, was the last part hydrogen or nitrogen?
Nitrogen.
Okay.
Let's move on to the next notebook.
All right, so in this notebook, which is much more complicated than the first one, we'll be estimating the ground state energy of the hydrogen molecule using the variational quantum eigensolver. So you'll be able to run a VQE calculation on the H2 molecule in the minimal basis. All right, so we do basic setup. We import the IonQ provider, and then all the necessary modules from Qiskit. Okay, so the first thing we need to do is we need to define the unitary coupled CCSC ansatz. For such a 2-electron 4-orbital problem, the UCCSC ansatz could be modeled by just one parameter, so that the ansatz looks like this. So the exponential I theta times this the polystrings, and it should be multiplied by the Hartree-Fock state. All right, so the next function is we need to form the electronic structure problem obtains the electronic Hamiltonian, and then transforms it with the Jordan-Wigner transformation. And we also diagonalize the Hamiltonian classically as a reference value. And then we now put things together. So the overall circuit is constructed by first we initialize the Hartree-Fock state, and then we apply the UCCSD on that, and then we just put these two together, and then get our overall circuits, the overall UCCSD variational circuits. Okay, so finally we define the classical optimizer. Here we use the Kobila optimizer, which is an optimizer that is provided by Qiskit. And then we pass the parameterized circuits into Qiskit's VQE function. So the Qiskit VQE function will perform the optimization for us. And then also it will perform the energy expectation value evaluation. And then we set the initial values for the parameters to be 0. All right, so now we can, so after we run this, we will print out the results and the optimized VQE energy. And now let's perform the VQE optimization on a simulator. Okay, so if you run it, it should be completed in like a second. It will print out the classical results, and then we'll print out the circuits, and you can see the circuit look like this. And then it will also print out the optimized VQE energy. As you can see that comparing this value to the classical results, the VQE gets is almost exact the same as the classical diagonalization results. And then we can plot the energy as a function of iterations, and you can see that as we at the optimization iterations, you can see that as we optimize, the energy eventually converges to the optimal, like the optimized VQE energy, which is this value. And one thing that you can see is that it will also print out the optimized eigenstate, and then so that's 0, 1, 0, 1. That's the Hartree-Fock state, which contains like more basically 99.5% of the overall wave function, and then it also have this 1, 0, 1, 0 state, which corresponds to a double excitation from the Hartree-Fock state that accounts for the correlation of the system. All right, so the last thing is we run the same thing on the actual IonQ hardware, and it will take a very long time to run because there are so many circuits to evaluate, and then each circuit is queued on its own individually. So I run it before, so it's done here. So here, as you can see, that we have the optimized VQE energy on actual quantum computer, and we can plot the energy as a function of the function of iteration. Now you can see that due to the noise on the QPU, it now converges to a much higher energy than that of the simulator. And another thing you can see is that it prints out the eigenstate of the optimized wave function, and it shows that the 0, 0, 0, 1, 0, 1 still the Hartree-Fock state is most of the wave function, but it contains a lot more of the states compared to like the simulator results. And a lot of these states are forbidden by symmetry. For example, if you look at this 0, 0, 0, 1, this state only contains 1 electron, but the system contains 2 electrons. So this is completely due to noise. And then some classical post selection, once used, could be able to get rid of these noises and improve the results. All right, so that's it. Any questions?
I found the PyCF does not work with the Windows very well. I heard like several the complaint about like they cannot install the PySCF with the Windows environments. I see you're using Mac, right?
Me, yes.
Yeah. I actually couldn't install this PySCF, which is the like sub-library of the Qiskit nature, so I was not able to do this.
Yeah, so I heard that that
So it looks
PySCF does not work quite well with Windows.
OS. So I have a question about this simulation. So we use the 4-qubit for this quantum simulation, which is the hydrogen molecule. So yeah, it seems straightforward that you use the like 4 qubit for the hydrogen molecule, but I just like wondering like the how many qubit we will need to simulate the larger molecule.
How many qubits? It depends on how many orbitals are there. Number of qubits will be the same as number of spin orbitals.
Yeah.
So
does it mean like we won't need like the thousands of qubits for just like kind of quantum cluster simulation, right?
Essentially, yes. So to simulate like problems like large molecules like the transition metal, like oxide catalyst, on that size of molecule, you will need 1,000 qubits to do that.
Mm-hmm.
The question is, I'm using Colab, and I have error in the second part. Is there a second part being just written in the chat? Is there any way to solve this issue?
Second part.
Second part is written in the chat.
I think this need to be
yeah, that there.
removed. Yeah.
I have a question about the calculation speed. I wonder whether the variational quantum eigensolver can boost the calculation speed of molecular dynamics.
Molecular dynamics. Are you talking about like the classical molecular dynamics?
Or molecular static. I mean just computational chemistry.
Yeah. So there are like multiple ways you can think of this problem. So like the for molecular dynamics simulations, for example, you essentially you need a force field to describe forces between atoms or molecules. And then for now, most the calculations for those force fields are done with, for example, a density functional calculation. So there are like opportunities for VQE to improve that force field. So like in general, VQE should be much more accurate than density functional calculation. So that in principle, you could replace that DFT calculation with VQE and get much more accurate force field. So that's one way to like for VQE to boost molecular dynamic simulation.
If there's any question about the like overall lecture today, just please yeah, ask any question. Yeah, thank you for your talk and thank you for all your effort for translation. Thank you.